Alright, what's up Year 10 students? Mr. Perry here giving you a run through of the entire Year 10 course so far for physics. So we start off, we did SI units. SI, they stood for System International. There were 7 of them. I can't remember what they all are, but you can look them up if you don't know them off the top of your head. We went on and we maybe talked about standard form. We said that if you want to multiply something by 1,000,000, you can multiply by 10 to the 6. If you want to multiply by 0.001, you can multiply by 10 to the minus 3. There are loads of different ways of talking about these. You have milli for 10 to the minus 3, you have micro for 10 to the minus 6, nano for 10 to the minus 9. Going the other way, we've got kilo is 10 to the 3, mega is 10 to the 6, and giga is 10 to the 9. Okay, so we kick off with our first equation, which is density equals mass divided by volume. This tells you, it's kind of like how heavy a substance is, but for a certain amount of volume. So it gives you an idea of what kind of objects will float or sink. Density is measured in kilogram per meter cubed. That's because mass is measured in kilograms and volume is measured in meter cubed. You could also give it in other units though, as long as it's still a mass and a volume, like grams per centimeter cubed is quite a common one. We must know how to rearrange our equations, and so mass is equal to density times volume, or maybe we want to know volume, so volume is equal to mass divided by density. You need to be able to apply that logic to any equation you come across. We talked about how we would measure the volume of something, and we could use something called a displacement cylinder for that. It's full of water, but when we put an object inside it, like this red ball, the water level goes up. The increase in the water level tells us the volume of the object. Otherwise, we're going back to math and we're doing a bit of volume is base times width times height. You multiply those 3 things together, that by that by that, then you're going to get the volume of the object. But that only works if it's like a cube or a cuboid, a nice object. Next we looked at how fast an object's travelling. So if I have a car like this, it's a very nice blue car, then it can move along with some speed. Okay, that speed can also be called velocity. That's talking about vectors instead of scalars, and we'll mention that in a little bit. But the equation for now is speed equals distance over time. Now this is the average speed, so if you know the total distance travelled, you know the total time taken, then you can work out the average speed for that time. Now speeds aren't always constant, sometimes speeds change, and if we have a changing speed we call that an acceleration. Acceleration is equal to the change in speed, which is v minus u, divided by the time taken. V is the final velocity, u is the starting velocity, and t is the length of time. Speed has a unit of meters per second, and acceleration has a unit of meters per second squared. And if you're wondering why it's squared, it's because we're dividing by time for a second time, and so we square the unit on the bottom. What about graphs then? Well, there are 2 main types. They both look like this, and quite often they both have a straight line like that. But the difference is that one is a velocity time graph, and one is a distance time graph, or a displacement time graph. There are a few things we need to know. If you find the gradient of this graph, the velocity time graph, that gives you the acceleration. However, if you find the area underneath the graph, so you draw down like that, and find out that area, that gives you the displacement, or the distance. With the distance time graph, it's a little bit different. If you find the gradient of the graph, it gives you the speed, or the velocity, and the area under the graph, well, that doesn't mean anything, so you should never be calculating the area of a distance time graph. So you might ask yourself, how fast does an object fall? And the fact is that it changes its speed all the time. Any object in Earth's gravitational field is accelerating, and we call that acceleration gravity. Gravity has a special number on Earth. It is 10, nice and convenient for us, and there are 2 units for that. One unit is the Newton per kilogram. The second unit is the meter per second squared. Now it doesn't really matter which one of those you use, but that leads us on to our next equation. So if I move that down there, we'll keep it there. Our next equation is the weight of an object is equal to the mass of that object times gravity. Now this is the first time we've introduced the concept of weight. It is a force, and it is therefore measured in newtons, capital N for that. Mass, of course, measured in kilograms, and gravity measured in newtons per kilogram, or meter per second squared. It always has a value of 10, so if you have an object that weighs 30 kilograms, that's 30 there, times a gravity of 10 on Earth, and the weight would be 300 newtons. If we were on a different planet, like the moon, well, the moon isn't a planet, but if we were on a different object like the moon, then the gravity on the moon would be much less. It's about 1.6, and so the weight would be less. The mass of an object is always constant in the entire universe. You take it anyway. You take your I'm trying to look around for something, my screwdriver on my desk here, I take that to any planet or even in the middle of space, it still has the same mass, but its weight changes. You should also have learned about vectors. So if I draw you another sketch of a car, there it is, lovely car there. It can move with a constant velocity in that direction, or it can move with an increasing velocity, it's accelerating. Or maybe I put some rocket boosters on the bottom of it, which fire out some fuel that way, and so the car moves like that. Now it has two components to its velocity. It has a horizontal component created by the engine, and it has a vertical component created by the rocket boosters. And what this allows me to do is figure out that it's actually going to move in this direction. So its overall velocity is in that direction. And this is called vector addition, I think. But it's certainly taking two vectors and combining them together to give one vector. The way we do it generally, if I can just move this stuff over here, the way we do it is we take the long one like this, then we might have another vector like that, and we measure these out to scale. Now what we do is we construct a parallelogram. Finally, we join up the two corner points of the parallelogram, and that is the length of our overall vector. It's a very complicated subject that you need to spend a lot of time practicing, so I'm not going to talk about it anymore here, other than to say that there are two types of quantity, scalars and vectors. Scalars are things that have a magnitude, vectors are things that have a magnitude and a direction. So for speed is a scalar, but velocity is a vector. Speed is a scalar, velocity is a vector. Distance is a scalar, displacement is a vector. Acceleration is always a vector, and you can argue about what time is. Time sits somewhere in the middle, and it's kind of still argued over, but I think it generally goes in the quantity of scalar. Okay. Next we look at moving in a circle. So if we take a top-down view of my car, and it's going round and round in a circle like this, and here's my car from above, then what we can say is that in order for it to go in the circle like this direction, there must be a couple of things going on. The main thing is that there must be something called a centripetal force, and that force acts towards the center of the circle. Okay? If it wasn't for that force, the car would keep going in a straight line. So if suddenly the centripetal force disappeared, the car would go that way, and that's a common exam question. The centripetal force tells us that there is a net force on the car, and we'll look at that in a little bit more detail in a couple of months. The net force tells us there is an acceleration, and I say to you, oh, well, it's going at constant speed, so how can there be an acceleration? And the answer to that question is, although it's moving at constant speed, its velocity is not constant. If its velocity is changing, it must be accelerating, and therefore any object moving in a circle is undergoing centripetal acceleration because it's accelerating towards the center of the circle. On to the next unit then. This is forces and pressure. This is what you've just done an exam on. You need to know the first equation from it. Moment equals force times distance. You've seen it before in year 9, so you should be kind of familiar with it. And what it basically says is if I have a pivot in the middle of a seesaw, and then I have a seesaw along here, and I have a person sat here, and a person sat here, if they are going to sit there and be happy and balanced, the system is in equilibrium. Now, I don't know if I can be bothered right now. Equilibrium. Equilibrium. That tells me that the object is not going to move in any kind of direction, like it's not going to accelerate in any direction. The conditions for that to happen are quite specific. It needs to have no net force. No net force. That means it's not accelerating upwards, flying into space. And it needs to have no net moment. And that means it's not increasing and rotating around faster and faster. Those two conditions happen, the object is in equilibrium. Remember as well, let's just make that a little bit bigger again, when we're doing the distance, we need to do the distance from the pivot, so we are talking for this guy here, we're talking that distance there. For this guy here, we're talking that distance there. There was a tricky question on the exam question, if we throw all that up there, that had the pivot here, then it had your bar over here, it had a downwards force here, an upwards force here, and remember you're looking that the distance for that force is there, the distance for the force on the left is all of that. So remember that this is an anti-clockwise moment, this is a clockwise moment, and if those two moments balance, there is no net moment. What I didn't mention there was the unit for the moment, and that's the Newton meter, because it's force times distance. That leads me on to stability. Stability involves having a box like this, and we need to define something called the centre of mass. The centre of mass is the point through which all of the weight can be said to act. So it's like, hey, imagine we didn't have a big rectangle stood on its end here. Imagine we had a single point of mass. That red dot is where the point would be. For simple objects like that, it's kind of in the center of the object. But if you've got something more complicated like this, the center of mass might actually be over here somewhere, not in the middle of the object. If I take an object such as a rectangle, and it's like that, and I try and tip it onto its side, the point it tips is the point at which its center of mass moves not through the old base, but through a new base. So its center of mass there is still just about through the old base, and if it kept on tipping, it would go through the new base. So I'll draw that again here. There's my object. I've made that one a little bit thinner, maybe a little bit taller, which will reduce its stability. If I tip it over to about that point and ignore the other one moving with it, we can see that the new center of mass, or the old center of mass, in fact, is now moving through a new base. Therefore, the new base will become this big, long, fat one, and it will sit there on the side like that. If we've got a spring, then we need to apply an equation called Hooke's law. And Hooke's law says that the force on a spring is directly proportional to the extension of the spring, or vice versa. The extension of a spring is proportional to the force on it. F equals kx. F, of course, represents the force, x is the extension, and k is called the spring constant. It tells you the stiffness of the spring. So if you imagine a spring that's really, really hard to compress or stretch, that would have a very, very high k value. If vice versa, of course, if it was an easy to pull spring, like a slinky or something, it would be a very low k value. We can look at our spring then here. There it is, like that. There's it extended, but if it wasn't extended, it would be, of course, like that. This is called the natural length of the spring, and this is the natural length plus the extension. Okay, so we need to be careful there with doing that. That all creates a nice graph for us, and it's up to you exactly how you do the graph. If we do it like this for the ease of it, then we'll put force on the y-axis and extension on the x-axis. Now that might make you think, hey, the dependent independent variables are the wrong way around there, but don't worry about it, it's cool, we can plot it that way around, and there are explanations why. We'll get a straight line. That's a straight line because it's directly proportional. It goes straight through the origin, and if we calculate the gradient of that line like that, that would give us k. If out of interest you had done x on the y-axis and f on the x-axis, then perhaps your gradient of the line would have been 1 divided by k, and it would have been a little bit more complicated to work out. We can also discuss a few extra things with the graph, so we'll just draw another one here. It's a straight line to start with, as we said, and that's because it follows Hooke's law. Extension is directly proportional to the force on it. But what we can see to happen, if we have extension here and force here, is that the line will start to slope up a little bit. That gives us 2 points on the graph that are of interest. The point where it stops being a straight line is called the limit of proportionality, and that's because the two things are no longer proportional. It doesn't quite fit, but you get the idea. That's because at that point it's no longer a straight line. The spring is not extending directly proportionally to the force, so we call it the limit of proportionality. The other interesting point is this point here. That's called the elastic limit, and at that point the spring will no longer return to its original length when we let it go. So those are 2 interesting points you need to know on the graph and be able to identify. So I said this was the forces and pressure topic, so we've done forces now, we should do some pressure, and pressure starts off by being defined by force divided by area, just like it was in year 9. Force is in newtons, area is in metre squared. That gives us a unit for pressure of Newton per metre squared. But that's just one unit, and physicists are kind of lazy sometimes. We can't be bothered saying Newton per metre squared, so we call that the Pascal. You can use either in the exam, it will not make a difference. Just be careful because you get kilopascals a lot here, so you're looking at 10 to the 3 pascals or 1,000 pascals you need to take into account. Again, checking we can rearrange those equations. If we rearrange that and we wanted F, we'd have F equals P times A. And if we rearranged it, we wanted A, we'd have F over P. Okay, so you need to be aware of how to rearrange those for every single equation, not just for this one. So we talk about P equals F over A, and that's the general expression for pressure, P equals F over A. It's almost like the definition of it. How much force is there over a certain area? We also, though, get pressure in a liquid. So if we have a lake like this, and there's my water, then we can say that the pressure at the bottom of the lake is equal to rho GH. Pressure equals rho GH. Now, rho is the density of the fluid, as we looked at the start of the unit, or the start of the whole chapters. G is gravity, so it's 10 newtons per kilogram, or 10 meter per second squared. And H is the height of the liquid. So if I want to know what the pressure is right down at the bottom here, I take the height that I am below the surface, I multiply it by the gravity, and I multiply it by the density of the fluid. That explains why the pressure in air is not actually that much, because although the depth of the air above us is huge, the density of the air is really, really tiny for air. For water, it's really, really big. So you don't need to go very deep before you get a lot of pressure. And if you take a look at the watch you're wearing right now, the one I'm wearing says that this is water resistant up to 200 meters. And that's because at 200 meters, the pressure will become too big and the watch glass will shatter. That'll be a problem for me if I need to tell the time at the bottom of the ocean. So that equation P equals, I need to get my pen. That equation P equals rho GH applies for fluids. Now fluids are liquids and gases. So if we just talk a little bit about gases, we might want to measure the pressure in a gas for different reasons. And we need to know two instruments that can be used to measure them. The first is the manometer. The manometer looks like this. It's like a pipe, and it has some fluid in it. Now it's normally mercury, but it also can be water, and those lines there represent the pressure on both sides is equal. This would be the pressure of a gas supply you're trying to measure, and this would normally be atmospheric pressure, the pressure due to the atmosphere. What happens then, if you turn the pressure of the gas supply up, then this liquid level moves down, and this one moves up. Or if it was the other way around, and you made the pressure of the gas low, then this side would move up, and this side would move down. And the height difference between them allows you to calculate the pressure. So that's for measuring the pressure of a gas, maybe like if you've been to Wockard and you've bought one of those gas containers because you've got a gas oven or something, or a gas barbecue. You could measure the pressure of that using this device. The other thing we have is a manometer. So sorry, that was the barometer. Let me spell that. That's the barometer. Then we'll make all of this small so we've got a bit more room. Let's go on to the manometer then. The manometer is a tall column of mercury. So let's represent my mercury by red, even though it's not red at all. And it might come up to about this far. Now, we've got atmospheric pressure pushing down on that mercury. This is open to the atmosphere. This bit in the top is a vacuum, so that means there's no air inside it. Just double checking the spell on a vacuum there. W, not W the letter, but two U's. That's a vacuum in there. As the pressure increases over here, the red line goes up, although it would actually be a grey line because it's mercury. That then tells us what the pressure is in the atmosphere around us every day, and that allows us to predict stuff like the weather and what the weather's going to be like. So next we talk about Boyles Law and gas pressure and volume. So if you're still with me, well done, because we're right at the end now. We start off with the equation then, PV equals constant. We could also state that as P1V1 equals P2V2. Or we could also mention that P is proportional to 1 over V. Those are all different forms of Boyles Law. Okay, so we'll stick them up here. Now check this out. This is a piston. The red thing is a piston and the black thing is a box. This is filled with gas particles, okay, so they're moving about with pressure. So you might say, hey, what happens then if I move the piston inwards? So there's my box again, move my piston to here. You can see that the amount of particles in every section is going to be much, much higher. And therefore, they're going to collide with the walls faster and harder and more often, and they're going to increase the pressure in the container. This is really looking at how we have decreased the volume, therefore we have increased the pressure. And that is pretty much Boyles Law. The one thing to mention is that the temperature throughout this, the temperature is constant. This must happen at constant temperature, and we'll look what happens as temperature impacts it in later lessons. And that pretty much brings us to the end of everything we've done in Year 10 Physics. Now, of course, I've spent less than 10 minutes going through that, and it's a lot more details. You know, there's a lot more to learn there by looking at your textbook and practicing questions, especially Cambridge IGCSE past paper questions. If you don't know where to find those, they're on Extreme Papers. Just type that into Google, Extreme Papers. But it starts with an X, which might be a little bit confusing. That has loads of papers, though, that you can download and then start practicing. Find the kind of questions that you're going to be asked so that you know the standard that we are looking for in this course. As a thank you and a well done for sticking with me, here's a picture to finish off. This is all of the available water and all of the available air that is on the Earth. So it's a pretty cool photo I found that gives you an idea of the scale of that liquid and that gas around our planet and how tiny they really are in comparison when you get them all together in individual spheres. Again, thanks very much for watching and good luck in physics over the next few weeks.